The problem states that a central horizontal section of a hook is a nice section with dimensions shown in the figure below this one here. This is a nice section here. The hook carries a load P. Well, the load line passes 60 millimeters from the inside edge of the section, meaning this one here. So this is the edge of the section, and this is this line. So here is where the load is applied. And the center of curvature being in the load line. So, okay, so this is the center of curvature, and then the load passes in this line. So what does it mean in the future when we are going to see this is that as I have to analyze this section based on the centroid of the section, then I know that a load applied here is going to carry a couple of effects. The first one being the load itself, and then a moment that the load is going to create because of the arm that I had to transit to come from the axis of curvature onto this point, which is the centroid of the area. Then they said determine the magnitude of the load P if the maximum stress in the hook is not to exceed the permissible stress of this number here, 108 newtons per square millimeters. So that's the first thing, and then the second thing would be that what will be the maximum compressive stress in the hook for that value of load. So I've written here, or drawn here, a figure where certain values from the geometry are needed. And these are important in order to find out the values for each one of these parameters that I'm going to need to find out how much is the maximum stresses, which then I would need to compare with this number to see if we are in the range or not. Then we need to have a value for the moment. That's an easy one because we have most of the data. Of course, we don't have the distance from the axis of curvature to the radius of curvature, so we need to calculate that. Then we don't have the area of this sort of eye section, which ends up being a composite section. I have a rectangle here, another rectangle here, and another rectangle here. So this eye section is formed by 3 rectangles. Then I need to calculate also what is the cross-section area, which we do have a formula for these type of cases. And finally, we need to decide at which points we need to evaluate these stresses to be the maximums, and obviously we need to evaluate them here and here. Now, because of the way it is proposed, what's happening here is that this section here is going to be subjected to tension, and this section here is going to be subjected to compression. And this load applied on this side is going to be trying to decrease the curvature, which means that the moment created by this load is going to be negative. Also, again, as a consequence of understanding how the load applied in this axis of curvature acts in this line where the centroid is that this load itself is going to create a direct stress, while the moment created by the load is going to create a bending stress, which is going to be defined by Winkle-Bach theory. So the first thing we need to do here is go for the easiest one. Of course, moment is the easiest one, but let's start understanding the area. Let's calculate the area of this element. And it's an area of a composite figure formed by 3 rectangles. So the area, that's right here, area calculation, we can start down here because we need to start populating these values that they are going to be important for the calculation of the cross-section constant. I'm going to start with the area of the cross-section. So let's start here, area of, looks like an O, cross-section. Here, yeah. And this area, as mentioned, is formed by those 3 rectangles. It's pretty easy to calculate. So it's going to be, now rectangles are defined by the shortest line is going to be, or side is going to be designated as T, and then the longer line is going to be designated as a base. So each of these areas, for example, this rectangle is formed by a T2, which is some sort of a thickness 2, and then a B2, which is a base 2. Those are the 2 designations we're going to use for each one of these areas. For example, this one is going to be designated by this B3 and then T3. And then this rectangle here is going to be designated by this B1 and T1. Okay? So let's do that. Let's start for the first one, and let's start for the left one. And that's going to be easy. I'm not going to write the dimensions, the units here, but I do going to keep track of them. So this is going to be 20 times 40, the first one, plus the other area, which is going to be 40 times 20 again. This is the one in the middle, 20 plus, and then the one on the right side is going to be 30 plus 6, times 60. If I said plus before, please forget about that, apologies. So this is going to be 60. Then the area is going to be, let's go to the calculator. It's going to be the total area of that compound figure, and it's going to be, I'm going to call it A, equal to 20 times 40 times or plus 40 times 20 plus 30 times 60. And that's 3,400 square millimeters. 3,400 square millimeters. Already found one of the values that we need for our formula that would allow us to calculate the bending stresses according to the Winkle-Bach theory. Second, let's try to calculate then what would be the centroid of this figure, because we need to know where the centroid is, as it is a compound figure. We know that the centroid is going to be located at some point here. And I already marked that, for example, the distance from the centroid, I call it G, to the edge, the one that is taken as a reference for the axis of curvature and the application of the load, is going to be y1, and then the other one is going to be y2. Now, we can calculate y1 using the first area theorem, and that's going to just allow us to locate precisely where is that centroid, just taking the moments of each one of these areas with respect to this axis of curvature. How do we do that? Well, for that purpose, we need to find out where are the centroids of each one of these figures. Put it here. So put it in blue. So this centroid, the centroid of the rightmost rectangle, the centroid of the center rectangle, and the centroid of the leftmost rectangle. So I'm going to call them in the same fashion, let's call it G1. And this is going to be G2, and this is going to be G3. Then let's take the first moment of area, to determine how much is this y1. And the formula for that, let's call it like this: first moment of areas. I tried to delete this using this feature, but first moment of area. So like this. And it's a formula that you well know that says that, for example, the position y times, oh boy, yeah, we got it. The sum of all areas equals to this part here, yi times ay. Then that position y is going to be basically taking this first moment of these areas like this, and then we divide that by the total area, which is A, already calculated. And if we substitute all the values in here, so let's start with the rightmost rectangle, which is this G2, and then that's going to be, what's the position of this centroid of this area with respect to this center here? Well, it's going to be, how much? It's going to be this 60 millimeters plus half of this 30 millimeters. So that's going to be, how much is that? 60 plus 15 is going to be, well, actually, if I'm taking this from the edge, well, I don't want to measure it from it, that's my bad. So I want to measure it from this. So how much is the moment of the areas from, or taking as a rotation axis, or axis of moment, axis of moment, this one here. So this is going to be just this distance, and this distance is half of this, which is going to be 15. So let's write down that. So it's going to be 50 millimeters times the area of this rightmost rectangle, which is 30 times 60. 30 times 60 plus the moment of this area here in the center, which is going to be, and let me mark here, the distance from the centroid all the way to the edge here, and this is going to be this 30 millimeters plus half of this 40, which is going to be 50 millimeters. And let me write it down here. It's going to be 50, I said, yeah, 50 millimeters times the area, and the area is 20 times 40, like this. Finally, the leftmost area is going to be the distance of the centroid, which is this one here, all the way up to here, and it's going to be 30 plus 40 plus 10, and that's going to give me 80. And then that's going to be 80 times the area of that leftmost rectangle, and that's going to be 20 plus, times 40. And all of this is going to be divided by the total area, which was calculated here, and it was 3,400 square millimeters. All this on the top is going to give me as units millimeters to the power of 3, because I have millimeters, so all of them is going to give me this, which means that in the end, one of these cancels out with this one, and the resultant unit is going to be millimeters here. So this y, let me change colors here. Oh, It didn't take it like this. Let's go to the calculator. And we have, I should give them names because I think I'm going to use them at some point. These kind of all of these values or figures or let's see. So I have, but well, we will do it when it comes. So, and that's going to be y1 actually. So the distance we're calculating using the first moment of area is going to be this distance here from the edge to the centroid of the composite figure. So it's going to be 15 times 30 times 60 plus 50 times 20 times 40 plus 80 times 20 times 40, and that's going to be divided by the area that I have it calculated. I have it there, and that's going to give me 38.5. Let's see here. 38.5 millimeters. This is this value here. I'm trying to write it down here, 38.5 millimeters. Now I can do a few population of these values, knowing that, for example, how much is going to be R then here? Well, R is going to be the sum of these 60 millimeters plus Y1. So I can write down here that R equals to 60 millimeters, which is going to be, let me just call it R1, because I'm going to need it later for sure. And then R is going to be R1 plus Y1, and that is 98.5 here. Green, yeah, 98.5 millimeters. Then I can also tackle R2. R2 is going to be 60 plus 30, and that's going to be 90 millimeters. R3 is going to be 60 plus, oh, actually it's going to be R2 plus 7 plus 40. Actually, I should write down here that R2 equals 90. Then R3 is going to be how much? It's going to be 60 plus 30 plus 40. R3 equals to R1 plus, I would say 30 plus 40. Yeah, 130, this one here. Finally, R4 is going to be R3 plus 20. Plus 20. And that is 150 millimeters. There we have it. Then another value I need to know is the value of Y2 here. And for that, I just need to subtract all this value here minus this one here. So Y2 is going to be equal to, I can do it, yeah, let's do it like this, 20 plus 40 plus 30, and that's going to be minus 38.5, and that's going to be equal to 51 point, yeah, this much, 5. 51, good, just move it a little bit, so I make space for it, so it's moving everything. Let me see if I can grab it, just this part, yes. Here, and then that's going to be equal to 51.5 millimeters. Now, having all these values, it is possible to calculate the cross-section constant for this case, and this is a value or a formula that is tabled or tabulated. It's right here, a cross-section constant. Like this. Then it's going to be H2, and it's going to be, and it is a long formula, but it makes sense the way it is written is R3 divided by A. And then here, this is where it is important to remember each one of these nomenclature we're using to define the areas of the composite region that we're working with. So we have here then B2 times the natural logarithm of here R2 divided by R1 plus T3 times the natural logarithm of R3 divided by R2, then plus B1 that multiplies the natural logarithm of R4 divided by R3, and all of this minus R to the square, like this. So we have all components. We only need to define how much is B2, for example, for our purposes here of the calculator, making it easier. So B2, we said it was 60. B3, I said it was 20. And B1, I said, or it's written here that it is B140. Then H2, I'm going to write like this. It's going to be R to the power of 3 divided by the area times, open brackets, B2 times the natural logarithm of R2 divided by R1 plus T3 times the natural logarithm, like this, of R3 divided by R2 plus B1 is the way I wrote it, yeah, times the natural logarithm of R4 divided by R3, and all of that is minus R squared. So let me check the formula again. So B2 is 60, then yeah, R2, 90, R1, yeah, it makes sense. Then T3, yeah, B1, perfect, and R2, just rechecking the formula here. All right, this is giving me here H, the cross-section constant, equal to 815.57 square millimeters. And this is a value I need. Then the other value I could calculate right away here is, for example, the value of the moment. And the value of the moment is bending moment here. It's going to be equal to moment is force P times the radius of curvature. Now, for this case, as this force is going to try to decrease the curvature, the moment is going to be negative. That's what we have worked with before. And this equals to the force we said is something that I don't know, and the radius of curvature is, how much is it? 98.5 millimeters. So I can keep working in millimeters because of the stress limits we are working here. So this is going to be actually then 90, how much is it? 98.5 P, and this is going to be in newtons, millimeters. This is and the reason this is done like this is because I don't know how much is that P. So that's the first question of the problem, that we need to find out what's the value of the P. So the stresses do not exceed this value here. Now, another thing that we need to calculate is, we said that as we have the load applied here, and we want to consider the effect of this load on an axis that crosses or passes by the centroidal axis of this figure, then this load is going to bring a direct stress and a bending stress. Let's calculate now the direct stress here. Then the direct stress, sigma d, is going to be equal to the load divided by the area of the section. Then again, I don't have the load, I don't know, that's an unknown, and then but I do have the area of the section, and that is 3,400 millimeters square. So, but I could write the units here on outside, like being like this. This one here, this is important, and then this other one here, which is important. Then I could, with the values I have at hand, populate this equation here, which is the equation for the bending stress. And you know already intuitively what we need to do, so we calculate the bending stresses, add it to the direct stresses, and then compare it here. And we're going to find out, for example, in these cases, that as the force is trying to pull apart the sections, meaning that it is exerting a tensile stress on the section, then the maximum stress is going to be the point, or it's going to be located at the point where the tensile stress is maximum, meaning that it's going to be located here. This point, we said that this is going to be in tension, here, tension, and this is going to be in compression. So as the direct stress is adding to the stresses already induced by the bending moment on the section, then the tensile stress is going to be maximum of all the stresses, and that's the one we need to compare with the permissible stress given here. For that, let's arrange a little bit kind of the bending stress formula here. Change colors. Bending stresses. Bending stresses, for example, I'm going to have 2 points. I'm going to call this A, the point A, and I'm going to call this point B. Then when I analyze these stresses, this is going to be from plus 51.5 millimeter all the way to minus 38.5 millimeters, because let's remember that this is my zero. This is the neutral axis, and then stresses start either increasing or decreasing depending on in which side of the neutral axis they are. Let me put here millimeters here. And we said that, again, just to keep in mind that maximum stresses are going to be located here. Max stresses is going to be located in here. This doesn't make sense here. It's writing stress like this. Then let's calculate the formula we're going to use for stresses. Let's simplify it a little bit, and we have it here. My general formula is going to be M, and we said that M was 98.5 P divided by the area. The area was 3,400 square millimeters times R, and R is 98.5 millimeters. Perfect. Then we are also going to have that this is going to multiply, this much is 1 plus R square, 98.5 millimeters square, divided by H, the cross-section constant, and that cross-section constant was 815.57. Then this is going to multiply AY, that I'm going to just carry there, and then I'm going to have this 98.5 here plus Y. So this is the formula we need to use. And the reason I did it like this is because I would like to group, for example, all these values, because I have an unknown here, and I want to group all of these values here. So let's do that. Let's build a general bending stress equation. And the first one is going to be 90. So it's going to be basically 1 divided by the area. So the first one, and that's it. That is this much. Yeah. Actually, I could write like this. Just trying to simplify things. 400. Because this is R. This one is R. This one is R. So P divided by the area. Then this multiplies. So I can do something more simpler here. And this is going to be, where's the mouse? Here. R squared divided by H2. And that's 11.90. 0.90. Then that's, I can divide that by this. Actually, I could do another, no, I cannot do any simplifications here. So I just need to write Y divided by this. 0.5 plus Y. Then let's calculate the stresses at point B. Sorry, yeah, at point B, which is where the maximum stress. Actually, I should write it here so we can have it as a comment. Maximum stress is at point B. And another change I'm going to make is that, just to avoid any confusion, this is bending stress at, I'm going to write like this, bending like this. Let me find a better way to do it. No, it's not direct stress, but let's do bending like this. And then this one also. So if the maximum stress is at B, then I could do something is just to gain some space. I can just delete this one. I'm not going to need it anymore because we already found out how much is that distance from the edge of the compound figure to the centroid. And I can move this a little bit up like this. Then let's see. If I consider that the maximum stress is going to happen, going to be max like this, stress is going to be at B, then that stress is going to be the sum of the direct stress plus the bending stress at B. And that's going to be equal to P divided by 3,400. Now I want to evaluate how much is this. I'm noticing that I'm missing one sign here because bending stress, this has to be negative because the moment is negative. So this is a minus here. So let's bring it to the calculator. I want to calculate or just take the resultant of what is in these big brackets. Let's bring it here. And then we're going to have, that is, actually I could divide minus 1 by 3,400. Yeah. Times then 1, and just excluding the p, plus 11.9 times minus y1 divided by r minus y1. And that's going to give me 0.0019 in here. Could have taken a factor, better factor, so this is 0.00195p. And that has to be equal, at least equal to this 108 newtons per square millimeters. Now, having this equation is pretty easy to just solve it, like directly, just isolating or using whatever method you would like to use. So we have, I'm going to call it x, then plus c actually times p, times x, because I'm calling p x, and then that's going to be equal to 108. And that means that the force is 48 kilonewtons. The load is P equal to 48 kilonewtons. And we have the first answer. Now, the second question is, what will be the maximum compressive stress in the hook for that value of load? Now that we have found the load, let's talk about maximum compressive stress. And we know that maximum compressive stress is going to be located at y equals to 51.5, which is the distance y2. And it's going to be located, it's going to be the sum of the direct stress and the bending stress at A, which is going to be equal to, then now that I found the load, it's going to be, we can keep it, I believe, in, let's write it as it should be, 48 times 3 newtons divided by the area, which is 3,400 square millimeters, plus then this bending stress, and we can calculate, we can use this formula again to calculate it now that we know the load P is 48,000. Now we can easily call it that the compressive stress at A due to bending is going to be equal to SA minus P divided by the area times 1 plus 11.9. I could apply the full formula if I wanted to, times Y2, which is positive, and then R plus Y2. And that's going to give me this much. And then that's the bending stress. Let me write it down here. Minus 71 point, minus 71 plus 0.786. And I could then sum the direct stress that I don't have it recorded here. This plus 48,000 divided by 3,400. We close down this. This is in newtons per square millimeter. Like this, then the maximum compressive stress, like this, compressive, is equal to minus 57.67 newtons per square millimeters. And this is the second answer to, or the last answer to the last question. To summarize a little bit of what we did, the beginning of the problem was dedicated just to determine certain values from the geometry which are needed to calculate the radius of curvature in the case of the centroid of the compound figure, and then also the cross-section constant, because we need those values to calculate as such parameters needed in the bending stresses formula. So we dedicated to the first part of the video of the solution to calculate the area, the centroid using the first moment of area, and then having those values we could proceed to calculate the cross-section constant, then the bending moment, which it gave me negative, and then this is a mistake, has to be negative here, but we corrected it after that. And it's negative because it tries to decrease the curvature at that moment. Then we know that because we have a load applied here, and then we want to know the effect of that load in this place, we need to take the load in a moment. The moment is going to create a bending moment, which is going to be generating a bending stress that we can calculate using Winkle-Bach theory. But then this load straight applied on the section is going to create a direct stress, which is going to be a tensile stress. This is why it's put like this. Then we want to calculate the bending stresses for points A and B, knowing that at point B is where the maximum stresses are going to exist. Knowing that, and knowing that the stress limit is this, we could calculate the load P, which was 48 kilonewtons. And after that, last question was what will be the maximum compressive stress in the hook, using that value of the load, and then just applying again the sum of the direct stress plus the bending stress at point A, it gave me that the compressive stresses at point A is minus 57.67 newtons per square millimeters. And this is the end of the problem. If you have any doubt or question, please leave it in the comments.